Okay, let's practice this again. I want you now to calculate the equilibrium constant for this reaction. Now, this is actually a reaction I got from your textbook, and what you need to do is use the appendix to find the half reactions. It's quite an involved table, and finally I found these two on the table. By the way, why don't you correct your notes? This is supposed to be a double parentheses here, so I want you to read around the one. So, look at these two half reactions with me. So notice, first of all, they're both reduction half reactions, not my favorite ones, but that's the way the text would list it. That's okay. You should be able to work with oxidation and reduction half reactions. So if you look at reaction number one, it's perfect for explaining where the oxygen is going to be on the left, the water is going to be on the left, and hydroxide is going to be on the right. So that's fine. Okay. Now, notice the copper half reaction. By default, I made a mistake here. This should be a positive too, so change your notes on that. So notice the copper plus 2 half reaction has to be switched around. Why is that? Because we want copper metal on the left. So, by the way, you know you're always going to have to switch one of the two around anyway. Okay, so if you switch the number 2 around, okay, that will give you the right overall reaction. But notice reaction number 2 also has to be doubled. So reaction 2 has to be doubled and reversed. So here it is double reversed. We needed to double it to get the electrons to cancel out, and also the overall reaction is supposed to have two coppers in it. So I reverse the sign on the E0, making it negative, but don't double it. Remember that it's pushed for voltage, so that doesn't change. Okay, so here's the overall reaction, and if you add up the two E0s together, you get the total E0 is the plus 0.06 volts. Okay, so I've written the Nernst equation, general form. And now, how does that change at equilibrium? Okay, the voltage is 0. Remember, no voltage in an equilibrium system. Okay, and E0 we found out is 0.06 minus 0.06 divided by, where did the 4 come from? It's a 4 electron exchange. And then the product of reactants is equal to the log of the K. Okay, plugging in some numbers now. So, what I did is I took the K term and put it on the left-hand side and divided 0.064 by 4. So I get a positive 0.015 times the log of K. The right-hand side will just be equal to the plus 0.06. So the log of K is equal to 0.06 divided by the plus 0.05, and that happens to equal 4. Okay, so the constant is equal to 1 times 10 to the positive 4. Okay, so pretty cool, right? So again, by using electrochemical table, we're able to get the equilibrium constant for a particular reaction. Okay, more practice. Okay, now on this one, I want you to do a little bit of work on your own. Oops, I messed up here. Okay, so I want you to figure out the reaction between zinc metal and iron. And I want you to use the electromotive table. Now, the zinc one's pretty obvious. Okay, you can find that on the table. Okay, so zinc goes to zinc plus 2 electrons, and the E0 is just a copy on the table. Now, here's the tricky one. What are you going to do about iron 2? Look at the table with me, because there are 2 half reactions involve iron 2. Okay, there's the one that I've written on there. It says iron 2 plus 2 electrons. I'm having trouble finding myself here. There it is. Okay, there's one really high. Okay, so iron 2 goes to iron goes to iron 2 plus 2 electrons. Now, notice I flipped it over. Why did I do that? Because when you have 2 half reactions off the table, one has to be reversed so the electrons cancel out. Now, here's a question I have for you. I want you to look way down on the chart, about 3/4 of the way down the chart, and you'll see iron 2 again, but it says iron 2 goes to iron 3 plus 1 electron. My question to you is, why don't you use that one? The answer is, remember on this table, you can't have 2 oxidation reactions. You have to have oxidation reduction. You have to flip one over. So if you take the iron 2 one and you flip it over, what happens is you get 2. You can't do that because you'll have two oxidation tables. Okay? So That's why you have to use the iron 2 going to iron 0. Okay, so anyway, you add the two together, and this is the overall reaction. Okay, so notice you have the two that I want on the left-hand side, zinc and iron 2. Okay, and then this would have to be the products that you get. Okay, you add the two E zeros together, and you get a voltage of plus 0.323 volts. Okay, now the goal is to find out the equilibrium constant for this reaction. So I've written the general Nernst equation above here. And then how does that change in equilibrium? 0 is the voltage, is equal to E0, which is plus 323, minus 0.06 divided by, notice it's a 2-electron exchange, and then the ratio, the mass action expression is the log of K. Okay, so here's the math. I brought the log term to the left, also divided 0.06 by 2, so I get plus 0.03 log K is equal to the 0. The log of K is 0.233 divided by 0.03. Let me try that on my calculator. So 0.323 divided by 0.03. Calculator automatically helpful, 0.323 divided by 0.03. I get an answer of 10.76. So K is 10 to that power. So second function 10 to the x is 5.84 times 10 to the 10th. Okay, last one to practice. Okay, so the goal is to calculate E0 if you have a transfer of 3 electrons and the equilibrium constant is given to you as 5 times 10 to the minus 2. So look at the Nernst equation with me. Okay, so how are we going to calculate the E0? Well, we're going to take the Nernst equation and let's write it as it would be at equilibrium, since we have the K. So I never gave you the voltage, but you know if you're at equilibrium, the voltage has to be 0. Okay, here's the thing we're going to try to solve for E0. Okay, 0.06 divided by, you're given that n is equal to 3 in this case. Okay, and the K is given to you, so the K will be 10 to the minus 5 times 10 to the minus 2. Okay, let's see how the math works out. Okay, so you're asked to calculate for E0, so I brought that on alone on one side, and the other side now becomes a positive 0.06 divided by 3 times the log of 5 times 10 to the minus 2. Okay, let's see how my calculator is working here. So I'm going to take 5e2 minus, hit my log button, get negative 1.3, and this will be times 0.02. And I get an answer of negative 0.26. Now, I want to discuss with you what is the significance of having a negative a negative value. Does this answer make sense? Okay. Now, first of all, E0 tells you what happens when the concentrations are 1 molar. So let's call this reaction AB. Okay. Now, why did Berg put the blue arrow going towards the left? Because a negative sign means the reaction is not spontaneous going forward, it's spontaneous going reverse. Okay, so the spontaneous reaction is B is going to go down, A is going to go up. Now, what does it mean to have an equilibrium constant of 10 to the negative power? It means that the product to reactants is small amount over large. Yeah, the reactant is the large number. So when the system reaches equilibrium, you're going to have a lot of A, a lot of reactant, and not much B. So hopefully that makes sense to you. Okay, so you've seen everything you need to know. Now you just have to practice it and learn it. So page 932, problem 67 through 72. Now in the homework assignment, the author is going to ask you to calculate the standard free energy. Laugh at them, you don't have to do that. Okay, so skip that particular part of this. But this is going to give you some good practice on what's going on. Okay, so that's all the lecture I have here for today.